Greetings! Welcome to Electronic Circuits 1. I am Razavi, and this is lecture number 39. Today we will talk a little more about the common source stage with degeneration and its input and output properties. Then we'll go to some biasing techniques and another interesting circuit topology. Before we go there, let's just refresh our memory about what we covered last time. Here's what we concluded. We looked at the common source stage with degeneration, with the resistor here tied between the source and ground. And we saw that this resistor reduces the sensitivity of the circuit to various factors such as temperature and process and supply voltage, etc. But it also reduces the gain of the circuit. As we can see in this equation with lambda equals 0, the gain is reduced because we have an RS in the denominator. And it is in fact this RS that tends to swamp out the variations in GM and give us a more stable gain. Now we also looked at the effect of degeneration on a current source. So if we build a current source and place a resistor from the source terminal to ground, then this current source becomes a better current source, in that its output impedance is higher. And the output impedance that we found was given by this very simple and elegant equation. And it says that it's, for example, we take RS and boost it by 1 plus GMRO, or we take RO and boost it by 1 plus GMRS. And that's the effect of degeneration on a current source. So with these things available, now we can go ahead and look at the input and output impedance of this common source stage with degeneration. All right, so for the input impedance, that's relatively straightforward because we know that the gate has a very high input impedance, at least at low frequencies. So let's look at the I/O impedances of the degenerated common source stage. So for the input impedance or resistance, we are looking into the gate. So we have something like this, and we're trying to measure this input impedance. So if we apply our test, our usual test, where we apply a small signal voltage Vx, measure the current, and of course in that case the supply voltage is at AC ground, then we see that this Ix is 0 at low frequencies. So we say Rin is infinity at low frequencies. At higher frequencies, we do need to worry about the capacitance between this gate and this channel, that C aux that we talked about before. But at lower frequencies, we don't have any appreciable current flowing through the gate. Okay, for the output impedance, let's see what we can do. Now, should we or should we not include a channel length modulation? Well, as I said last time, when we are finding the voltage gain of the circuit from here to here, we at least in this course, neglect channel length modulation, because with channel length modulation, the gain expression is more complicated, and in fact, I don't even remember it. For the output impedance, we can still neglect channel length modulation, but we don't have to. The results are not that complicated. So let's be more thorough and include channel length modulation. All right, so let's assume that lambda is not 0 and see what we get. All right, so here's the situation. We have a common source stage with degeneration, and to find this output impedance, we set all independent sources inside the circuit to 0. So the input voltage source goes to 0, the supply goes to 0, and now we come from outside and apply a small signal voltage source Vx, and we would like to measure Ix. This resistor is Rd, this one Rs. So that is the circuit that we need to solve. Now we could draw everything, the small signal model and everything, and solve the circuit. But actually, from the results that we found before, we can readily find this output resistance. So here's the way to think about it. First of all, RD goes from here to ground, right? So why don't we change the color of our pen and cross this out here and draw it like so. Right, the circuit hasn't changed. I just redrew it because it's easier to visualize what's happening now. All right, so what we see is that this voltage source sees a resistance from here to ground. Okay, so the voltage source sees at least this RD, and then in parallel with this RD, it sees some other stuff. Why in parallel? Because this other stuff can go into a box with two terminals, like so. And we see that there are only two wires coming out, this one and the ground wire. So I can replace this box with a two-terminal impedance. And what we see is that that two-terminal impedance also goes from here to ground. So that two-terminal device is in parallel with RD. Okay, this box is familiar to us. We analyzed this last time, and we found that the impedance measured between the drain and AC ground of a degenerated current source is given by this expression, which I just showed you, right? So in this, we use this symbol, an arrow, to indicate the impedance of this guy between these two terminals. And in this measurement, the gate is at AC ground. So we have this equation for the impedance of this entire box as far as these two terminals are concerned. So we're going to use that for this box here. Okay, so this is what we get. I replace this box with that impedance. Here's the impedance. Its value is 1 plus GMRO times RS plus RO. So this represents this dashed box. And then I have RD. So then I have RD. And then I have the voltage source. So now we see that Vx over Ix will be just the parallel combination of RD and this impedance. We don't have to draw the small signal model and write KVLs and KCLs. We build upon everything that we have learned in the past to solve more complex circuits. All right, so this means that the output impedance of the common source stage with degeneration is equal to RD, but not RD alone, in parallel with some other stuff. And it's that stuff here. So it's 1 plus GMRO times RS plus RO. So if you remember, in the common source stage without degeneration, when we included channel length modulation, the output impedance was RD in parallel with RO. But now, because of degeneration, that RO does not directly appear between drain and AC ground. Instead, this whole thing is replaced by this expression. So that's what we get for the output impedance of the common source stage with degeneration if we wish to include channel length modulation. If not, then this whole thing is infinite. We just have RD, right? Because this is infinite, so this goes away. We just have RD. So depending on how much accuracy we're looking for in our calculations, we can include one of the two. Very well. So these were the input and output impedances of the common source stage with degeneration. And we are now ready to go on to biasing techniques. All right, so let me go over here and talk about biasing techniques for the common source stage. Well, so far, whenever we talked about a healthy common source stage, we drew something like this. We said we have a transistor serving as an amplifier, and then we have an input maybe from a microphone, just as an example. Now, to keep the transistor on and have a reasonable current flowing through it, we apply a battery here between the gate and the source, which we call V0. And then to ensure that this device is also in saturation, remember all the different examples that we went through until we got here, to ensure that this device is saturation, meaning that the drain voltage is reasonable and a current can flow this way through the device, the bias current, we have a battery here and here. So that's what we call, for example, VDD. Okay, so this circuit, as shown, can be properly biased. In the absence of a signal from the microphone, you have a certain voltage here, you have a certain current here. Hopefully this VDS is not too low, the device is in saturation, everything is good, we have an amplifier. But the problem is that if we have many of these amplifiers around, we don't want to have so many batteries connected to their gates, right? Where do we get these batteries? We are allowed to have one battery for the entire system, and that would be this guy. This is the power supply. It could be a battery, it could be a charger, or something along those lines. But we don't want to have these little batteries for every stage in the circuit. So somehow we have to think of a circuit that can serve this purpose, can generate a voltage equal to V0. All right, so we're looking for a circuit, a very simple circuit, that generates a constant value of V0, and it probably has to feed from this battery. So what we are thinking is the following. Let's take that battery voltage. So remember, we draw a thick line here, call it VDD, which is just this battery here. So I'll draw this battery over here just so that you know we still have it, even though we usually don't draw it. So this is the battery. And I'm hoping to create this DC voltage from the battery voltage. So for example, the battery voltage is 2 volts, and I would like to generate 0.8 volts for this V0. So how do I do that? Well, from basic circuit theory, you remember that we had something called a resistive divider. And that does that. It takes 2 volts and gives you 0.8 volts. So I will take a resistive divider from the battery voltage, call this R1 and R2, and choose these values so that this voltage at this point with respect to ground is 0.8 volts. Now I can give this to the gate of the MOS device. And then I still have the rest of the circuitry, and this circuit is now biased without having a battery for the gate network. The gate is simply biased by a resistive divider. So that seems like a simple approach that we can repeat for all of the stages in the circuit. Every stage would have its own resistive divider and would provide some amount of voltage necessary for the gate of this device. So we can do that. All right, that's good. That's a very basic circuit for biasing. In fact, this is not very commonly used in integrated circuits where we have many of these MOSFETs and many of these stages. But at least for now, to get our feet wet and for us to familiarize ourselves, that's fine. All right, well, when we have a situation like this, here's what we're hoping. So if this is V0, we're hoping to get V0 here. So we have to choose R2 over R1 plus R2 times VDD equals V0. So if I have a V0 in mind, I choose these resistors to give me that amount. So that voltage is now good to go to the gate of the transistor. Okay, so now for this type of biasing, we have some interesting effects that arise, so we have to look at them one by one. So let me make some observations to show you what we need to worry about now that we are biasing the circuit. All right, so observations. Number one, let's find the input impedance of the common source stage with this resistive divider biasing it. So here, use the circuit, and I would like to find the input impedance. What do? Well, as usual, we go ahead and set the independent sources to 0. We apply a voltage from outside, Vx, measure Ix, that would be the input impedance. So let's do that. If I set this rail to 0, then R1 goes from this node to ground, just like RD goes from this node to ground. So let me draw that like this. I have R1 going to ground, R2 is already going to ground, then I have the transistor itself. I don't bother to draw the small signal model, and then I have RD going to ground, right? That is the model of the circuit ready for input impedance calculation. And then I apply Vx here, and I would like to measure Ix. Now what you remember from last time and also from this calculation here is that the input impedance of the common source stage is ordinarily infinite, but not anymore. As you can see here, now we have these two resistors, sorry, this is R2. We have these two resistors that are loading the input, meaning that the input impedance now has fallen from infinity to R1 in parallel with R2. The gate still doesn't draw a current at low frequencies, so that's still infinite. But we have infinite in parallel with R2, in parallel with R1. So in this case, Rin has fallen to R1 in parallel with R2. So is that a good thing or a bad thing, the fact that the input impedance has fallen? Well, generally for this common source stage, it's a bad thing. Let me give you an example of how that happens. All right, so let's go ahead and connect our microphone to this amplifier, just like we did before. But let's assume that the microphone has a more realistic model. A realistic model of a microphone is not just an ideal voltage source. This microphone here has some internal resistance. If you remember in basic circuits, when we consider like a battery, we said a battery has some internal resistance. It's really a Thevenin equivalent, so there is some internal resistance. So when I try to model the microphone more realistically, this is what I have. I have a voltage source, and then I have a resistance. So we'll call this R mic, and this is what we usually call Vin. That is the model of the microphone. This mic resistance might be, depending on the design, the type of microphone, it might be 300 ohms, 100 ohms, or higher. So it's some value. Okay, now we connect this microphone to this circuit here with the biasing elements in place. So here's what we have. We have R1 in parallel with R2, these two together. Then we have the transistor and the load resistor, RD. And we would like to find the voltage gain of the circuit. We would like to find V out over V in. Okay, so this looks a little complicated, but we don't have to draw the small signal model of the MOSFET for this calculation. We'll see how that goes. And again, let's assume lambda is 0 just for simplicity. Okay, well, let's call this node X. Now, rather than try to find the effect of V in directly at V out, I will do it like this. I will say, let's find the effect of V in at this node first, and then let's find the effect of this voltage at this output. And by that, I really mean the following. We can say that V out over V in, which is what we are looking for, is equal to this voltage over this voltage is equal to Vx over V in times V out over Vx. So So this is like the chain rule that we learned in calculus. Okay, how much is Vx over Vin? That's this voltage over this voltage. We recognize that this is a resistive divider, so it attenuates Vin by some amount. So we write Vx over Vin is equal to this resistor over the sum of these resistors multiplied by Vin. So R1 in parallel with R2 over R1 in parallel with R2 plus R mic times, so that's Vx over Vin, the voltage gain attenuation from here to here. Now how much is V out over Vx? V out over Vx is like this. That's of course well known. It's a simple common source stage. So for that we write minus GM/RD. So this is the overall voltage gain from the microphone all the way to the output. One note of caution. When we say V out over Vx, in that calculation, what we really mean is we come in and apply an ideal voltage source from node X to ground and find its effect at V out. That is the definition of V out over Vx. In other words, when you're calculating V out over Vx, you need not worry about this resistor here or this resistor here. They play no role in V out over Vx, because for that test, when you are to calculate V out over Vx, in your head you're actually placing an ideal voltage source from here to ground, an ideal AC voltage source. So that completely overrides these resistors. These resistors play no role in V out over Vx. They play a role only in Vx over Vn. Okay, so what we see here is that we have an attenuation factor as a result of these two bias components. If we didn't have the bias components at all, R1 over R1 in parallel with R2 would be infinity. There would be no attenuation between the microphone and R1 and R2. But now we have some attenuation. So that is the result of using these resistors to bias the gate of the device, right? We have to do that. So from that perspective, we would like to choose R1 and R2 as large as possible. In this case, what we do need to do is just make sure R1 in parallel with R2 must be much greater than R mic, maybe 10 times. So we can say choose R1 in parallel with R2 to be much greater than R mic to minimize the attenuation. So, and sometimes that's possible. If the microphone resistance is only a few hundred ohms, that's not a big deal. They can do that. But that's a condition we have to remember. These biasing components load the microphone because they create attenuation. Okay, next observation is as follows. The next observation, if you go back to the original circuit here, is can I increase RD indefinitely? Because I'm thinking that the gain of the circuit is GM times RD, for example, this part of the circuit, right? So to maximize the gain of the circuit, I would like to maximize RD. So let's see what exactly we encounter in terms of just bias conditions. So from the small signal point of view, from the amplification point of view, we would like to maximize RD. But will something go wrong as RD increases? So can we increase RD to increase the gain? Well, perhaps to some extent, but RD cannot just become larger and larger. Why is that? Well, let's look at this part of circuit again carefully. And let me change the color of my pen. So here's the situation. We have a circuit, and in the absence of a microphone signal, we know that this voltage is equal to V0. So this is V0 with respect to ground, and then we have a resistor here and a power supply VDD. All right. Well, I chose some RD, I got some gain, let's say a gain of 2. It wasn't enough. So I decided to increase RD. So if RD increases, what happens? Well, then this voltage comes down. We know that the bias voltage at the drain is equal to VDD minus ID times RD. So as I increase RD, the voltage drop from here to here increases. As this voltage drop increases and the top terminal is fixed, the bottom terminal comes down, which means the drain of the MOSFET comes down, which means the MOSFET comes closer to triode region. So in other words, if you look at the characteristics of the MOSFET, ID versus VDS, as we increase RD, the drain voltage falls. As the drain voltage falls, VDS falls, so we are traveling this way. And eventually, we get into the triode region, which is undesirable because the GM drops, everything goes bad. So we can increase RD only to the point where the drain voltage is below the gate by only one threshold voltage, no more. So if the gate voltage is here, the drain can come down to one threshold difference and then has to stop. If it goes any farther, the device will go into the triode region, the gain drops. So in this case, we can say that this voltage has to be greater than or equal to the gate voltage minus one threshold. That's the limit, V0 minus VTH, for the device to stay in saturation. So that readily tells us how much RD should be, right? So we can say that VDD minus V0 plus VTH divided by ID has to be like so. That's the upper limit on RD. If RD is larger than this value, then this voltage is too low, the device is in saturation, the device in triode region, we have a problem. So that was observation number 2. These are all related to biasing. Even before we consider the small signal operation of the circuit, we have to make sure that the transistor is healthy. And by healthy, we mean it's in saturation, it has the right amount of current, etc. So this condition has to hold before we call it a good amplifier and proceed to analyze its small signal properties. Very well, let's go to the next observation. Okay, observation number 3. The next question that we want to raise is the following. So let's say I have designed my amplifier like this. So I chose R1 and R2 accordingly. So we don't have to have degeneration for now. So I have chosen R1 and R2 properly. I have chosen RD properly. We're good to go. R1, R2, and this is the output voltage. And that's the power supply. And I decide to use this, for example, in a Bluetooth receiver. So remember what the Bluetooth receiver looks like. Here's the diagram that we developed a long time ago for the Bluetooth receiver. What we saw was that we had an antenna that picks up the signal that's coming in from some other transmitter. Then we go through a low noise amplifier. So maybe I can use this common source stage as a low noise amplifier. And then other types of processing. So, okay, so let's do that. Let's try to use the common source stage as a low noise amplifier connected to the antenna. And I would like to bring an antenna and connect it to here, okay? All right. So I go look around, find an antenna that works maybe at 2.4 gigahertz for Bluetooth. And I come up with something like this. This is called a loop antenna. As you can see, it's a loop. And I would like to connect this to my LNA, to my amplifier, to amplify the signal that I receive from elsewhere. All right, so here's what we're going to do. I'm going to take this and connect it from here to ground, right? So one terminal connects to the input, one terminal connects to ground. Okay, I hope you can see the details of the antenna has 2 pins, and the 2 pins are connected like this. Now, do we have a problem? Okay, so if you look carefully, this is what we see. Before the antenna has any signal, do we have proper bias conditions? You can see that this node, which was supposed to have a voltage of V0, now goes through this wire, and comes to ground. In other words, the antenna is creating a short circuit between the input of the LNA and ground in the absence of signals, right? This is just a wire, piece of wire, right? When there's no signal, this is just a piece of wire. So what the antenna did was short the input to ground. And now we have a problem, because obviously this voltage is now 0, not V0, the voltage necessary to keep the transistor on and healthy. So the device is off, the circuit's dead, hopeless. So what do we do in that situation? If whatever we're connecting here, a microphone, an antenna, any other device, wants to short this to 0 at DC, meaning without any signals, then it kills the bias of the circuit. Well, the simplest solution in that case would be to add a capacitor here to isolate the DC levels from each other. So we would add a capacitor right here. So now we know that a capacitor is an open circuit as far as DC levels are concerned. So as far as biasing is concerned, we have V0 because R1 and R2 are generating that. There's no DC current this way, so we're good. And this antenna doesn't bother this node because this capacitor blocks the DC connection. And when the signal comes in, this antenna produces a signal at this point. That signal can go through this capacitor if the capacitor value is large enough. If you remember, the impedance of a capacitor is given by 1 over C omega. So if C is large enough, this impedance is small. So the capacitor looks like a short circuit for signal frequencies. So signal goes through, the DC doesn't go either way, we're good. So that's a quick fix of this type of situation. All right, so what this tells us is the following. Anytime we have an amplifier, or any circuit for that matter, that has some bias conditions, and we want to drive it with something, drive it by an antenna, or a microphone, or another amplifier, we have to worry about disagreement between the bias that this guy needs here and the condition that the preceding stage or the preceding device produces. There could be disagreement. Here the disagreement is that the antenna wants to see 0 volts here at DC. This guy doesn't like 0 volts. So it could be other situations. For example, what if we have an amplifier like so, and then this amplifier is driving this amplifier. Okay? So I need 2 amplifiers. I need 2 amplifiers like so. And I would like to connect the output of this guy to the input of this guy. Why do I do that? Why do I have 2 amplifiers? Well, this is what we call cascaded amplification, meaning the first amplifier provides some gain, and the second amplifier provides more gain. These 2 gains will be multiplied. So if the first stage produces a gain of 5 and the second stage gain produces a gain of 4, we have a gain of 20 from here to here. So that's better than having one stage. Sometimes we have to do that. So now, if we have a situation like this, are we sure that this bias required for this gate and this bias required for this device to be in saturation agree with each other? Maybe they don't. Then, if that's the case, place a capacitor between these two. That's one solution to avoid this problem. So anytime we have a stage and we want to connect it to the outside world, to another stage here, another stage here, we have to worry about that. We have to worry about where it's connected at the output. We have to worry about where it's connected at the input. All of these matter in terms of biasing. If the bias is incorrect, of course the circuit will not work very well. All right, so that was observation number 3. And finally, one more observation. If we look at this voltage that we generated here, V0, and then try to find the bias current of this device, this is what we see. We have ID, assuming it's in saturation, and neglecting channel length modulation, is equal to 1/2 of mu n C ox W over L VGS. VGS minus VTH, right? VGS happens to be V0. So V0, which is actually the result of this division. So let me write that as VDD times R2 over R1 plus R2. So this whole thing is V0. Then minus VTH of the MOSFET, and then squared. This is the amount of current that flows through this device as a result of this type of biasing at the gate, provided that we are in saturation. Okay, this equation says that the bias current of the MOSFET is sensitive to some parameters. We see that it's sensitive, so sensitive to supply voltage here. So VDD. Process. Process means parameters that may vary from one wafer to the next wafer. Those include mu n, generally mu n Cox and VTH. So mu n Cox and VTH. The threshold of the MOSFETs also can vary from one wafer to another wafer. And then temperature. Temperature, because mu n Cox can vary with temperature, mu n can vary with temperature, VTH can also vary with temperature. So we have these sensitivities to these parameters. So generally this is not a very stable circuit in terms of its bias conditions. If the bias conditions vary a lot, then GM and RO vary a lot, so the parameters, the performance of the circuit varies. Okay, all right, so now that we made these observations, let's go ahead and look at the common source stage with degeneration. So reduced sensitivity with degenerated CS stage. So to alleviate these problems, we will go ahead and use a degenerated common source stage here. So let's go change the color to maybe red again. And here's what we will do. We add some degeneration in the source, and then the rest of the circuit is the same as before. So why is it that this degeneration helps reduce these sensitivities? Well, remember what we said before. We said that if the gate of this device is perturbed by some amount, delta V, then this VGS does not change by delta V. It changes by less than delta V. And that means that this current has less sensitivity to that delta V. So it's the same situation here. For example, if the supply goes up, if VDD goes up, and this V0 wants to go up by a small amount, well, this circuit is less sensitive to that change than this circuit, right? Here, if V0 goes up by delta V, VGS changes by delta V. Whereas here, if V0 goes up by delta V, this VGS does not change by as much as delta V. It changes by less than delta V. So this circuit is less sensitive to these variations than that one. So sometimes we use this. Again, in integrated circuit design, even this one is not very common. But at least it gives us some feeling for what we need to do. Okay. All right, so given the circuit, how do we calculate the bias conditions? Well, it shouldn't be that hard. As usual, we start out knowing that we know this voltage here is the result of division between the supply and between these two resistors. So we say this voltage is VDD times R2 over R1 plus R2. Okay, so that's the voltage we have here. Previously, remember, we had a voltage source we called V0, so this is similar to that. Now we can write a KVL around this loop. We can say this voltage, VDD times R2 over R2 plus R1, this voltage is equal to this voltage, VGS, plus this voltage. And we know how much this voltage is because ID flows through RS. So we can say this is equal to VGS plus ID times RS plus ID times RS. Okay, so that's one equation. We have two unknowns, ID and VGS, but we have one more equation that relates ID and VGS themselves according to this MOS device. So for that we have ID is equal to 1/2 of mu n C ox W over L, then VGS minus VTH squared, again assuming that channel length modulation is negligible. So for a given MOS device, we know mu and C ox, W over L, and VTH. These are properties of the MOS device. So these two equations, we can find VGS and ID, so we have all the properties of the circuit. Of course, we always have to make sure that the device is in saturation. So after finding ID, which assumes saturation, we go back and find VDD minus RDID and make sure that this drain is not too low compared to the gate voltage. Okay, so that is the use of degeneration to stabilize the bias. Let's look at one more type of circuit that tries to reduce these sensitivities. We will call this the self-biased CS stage. This stage has a somewhat wider application than these other circuits we saw in integrated circuit design. Sometimes we use this, and it looks like this. We take our simple common source stage. Now we need some sort of voltage for the gate, right? To ensure that the gate source voltage is high enough for the device to carry a current. Now, rather than derive that voltage from the supply, we do it like this. We connect a resistor between the gate and the drain. We call this self-biased, meaning that it's biasing itself, not from VDD. So this circuit has many interesting properties, which you might learn in more advanced courses. But let's just see how this operates and why it should be less sensitive than these circuits, especially this circuit, to these variations. Well, okay, so let's say, as an example, that we build the circuit on wafers. We try one wafer today, we try another wafer tomorrow. And the only thing that changes from one wafer to another, as an example, is the threshold voltage of this device. Let's suppose everything else is constant, it's just the threshold voltage. So now what happens? Well, let's say that on wafer number 1, the threshold voltage was 0.5 volts. But when we went to wafer number 2, the threshold voltage became smaller, 0.45 maybe, 50 millivolts less. So then what happens? Well, because the threshold voltage is less, we expect that the current wants to increase. All right, so we expect that the device now wants to draw a larger current. Okay, so let's say it does that. If the device draws a larger current, so let me write these step by step. So VTH goes down from one wafer to another. That means that ID wants to go up. Okay, well, if ID goes up, if this current goes up, then what happens? We draw a larger current through RD, so this node voltage wants to come down. So this voltage wants to go down. If this voltage goes down, what happens to the gate voltage? Well, the gate voltage and the drain voltage, as far as the signal is concerned, are exactly equal. As far as the bias is concerned, are exactly equal. Why? Because you can see that there is no current going through the gate. The current through RF is 0. The voltage across RF is 0. That means that this voltage and this voltage are equal. So if the drain voltage goes down because the current increases, then the gate voltage also goes down. If the gate voltage goes down, if it just goes down, the current wants to go down. So there's a self-correction mechanism in the circuit. If the threshold goes down, the drain current wants to increase. But if the drain current wants to increase, this voltage wants to drop. If this voltage drops, then the gate voltage drops, meaning that VGS drops, so the current drops. So the change in the current is less than the previous cases, for example, for a given change in the threshold voltage of the device. All right, that's one example to show that this circuit is less sensitive to these variations than these previous circuits. Okay, now how do we analyze this? How do we find the bias conditions for the circuit? Well, it's not that hard. Again, as usual, we say that, let's say we have a current ID here. We know that the drain voltage is equal to VDD minus RDID. So we say the drain voltage is equal to VDD minus ID RD. All right. Okay, now it just happens that in this circuit, the gate voltage and the drain voltage are equal for biasing calculations, right? So that means that this is equal to the gate voltage. And this happens because the gate draws no current, RF has no current, the voltage across RF is 0. All right, this is the gate voltage with respect to ground. This is VGS. So I can find ID. I can say ID is equal to 1/2 of mu n C aux W over L. The gate voltage, VDD, minus ID times RD, minus VTH, VGS minus VTH, squared. Again, assuming that lambda is 0. So now this equation is very easy. Just we have one unknown ID, and solve it, find ID. We find ID, we find VGS, then we can find VDS, because VDS is equal to VDD minus ID RD. And of course, eventually we have to make sure that the device is in saturation. Or do we? Well, interestingly, in this circuit, the device is guaranteed to be in saturation. Why? I'll give you 90 seconds to think about that. That's the quiz of today. Okay, so why is this device always in saturation? Well, remember, for saturation to happen, you have to make sure that the drain does not go below the gate too much. Well, in this case, the drain and the gate are equal, as you can see here. So if the drain and the gate are equal, the drain can never go below the gate voltage, so the device is always in saturation. So that's the beauty of this self-biased stage. It guarantees that the MOS device is in saturation. Okay, so let's look at one example of circuits that we can analyze here. All right, so let's look at an example. And let's suppose we have something like this. We have a common source stage like this, and then we have another common source stage like this. So RD1, RS, M1, M2, RD2, and for example, for this guy we have the usual biasing. That's okay, R1 and R2. And I would like to attach these two stages. I would like to cascade two stages. So that's what we call cascaded amplifiers. Cascaded stages. Okay, as I said before, the purpose of cascading is to increase the voltage gain. This circuit provides some gain. This provides some other gain. When we cascade them, when this is connected to this one, the overall gain will be higher. Now, the only question we have is how to connect these two. Previously, we said, well, we can bias the second stage independently and then place a capacitor between them. That's one possibility. In integrated circuits, we don't do this very often because this capacitor becomes a large device. And as you know, the cost of a chip is proportional to the area of the chip. So the larger this capacitor, the more expensive it will be. So sometimes we have to do that, but sometimes we don't. And to avoid using that capacitor, what we try to do is we design this circuit so that its drain bias voltage is agreeable with what the gate voltage of this should be. So let's say we design the stage and we said the gate voltage should be 0.8 volts. Then we go ahead and design this circuit such that the bias voltage at the drain is also 0.8 volts. And now we just connect them directly because the two biases agree. So then we connect them together, and these two are biased at the same time together. So we can do that. Now, why did I use degeneration here? This is just as an example. You can have degeneration here or both. It doesn't matter, but just one example. So in this example, we would like to find the voltage gain of the overall circuit with lambda equals 0. So in these cascaded structures, the way we do it is that we call this node X, and as usual, we say, if we are interested in V out over V in, so we say V out over V in is equal to Vx over V in times V out over Vx. And then we go ahead and find each of these separately, and then we multiply them. So how much is Vx over V in? That's the voltage gain from here to here. Well, we know that for a common source stage with degeneration, right? We derived this last time, if lambda is 0. So that is the gain of a common source stage with degeneration. We said is equal to minus the total resistance tied between the drain and AC ground, that's RD1, divided by 1 over Gm of the transistor, so 1 over Gm1, plus the total resistance tied between the source and AC ground, so between here and here. Okay, that takes care of Vx over Vn. Now, for V out over Vx, we have this stage. So that's even simpler. That's just a simple common source stage. So for that, we have minus Gm2 times RD2. And this is the overall voltage gain of that cascade. So we just have to be comfortable with these calculations. Very well. Okay, so we have a few minutes. I will introduce the common gate stage now, and then I will analyze it more carefully in the next lecture. So let's talk about the common gate topology. The common source stage and its variants provide some sort of performance when we are using them in different applications. Now, sometimes we want a different type of performance, and in that case, a common gate topology might be a better choice. So, in most applications that you see, the common source topology that we've seen and its variants are used for about 90% of the cases, maybe even 95% of the cases. But there are some 5 to 10% of cases where a common gate stage is preferable. So that's why we study the stage as well. The common gate stage is defined as following. We have a transistor with a load resistor, like so. And the input is applied to the source of the device. In the common source stage, the input was applied to the gate of the device. But here, it is applied to the source of the device. So V in goes here. So we define it as input applied to source, and the output is taken at the drain of the device, like in the previous case. So the output is here with respect to ground. So we say output sensed or taken at the drain. That is the definition of a common gate stage. What do we do with the gate? The gate doesn't receive a signal. Well, we have to connect it to some bias component. After all, this device must be biased correctly. So for now, let's just connect a battery here and call it something, V0 or whatever we want. We need some sort of biasing there. And this is a common gate stage. So it's a little different from the common source stage because the input is not applied to the gate, is applied to the source. And we will see that this has some interesting implications in the design. The gain of the circuit looks a little different. and the input impedance of the circuit looks a little different. So those are interesting differences between this topology and the common source topology. Okay, so what we need to do for this type of circuit is twofold, as we've seen in the past. So step one, perform bias calculations. Remember that we always have to start with bias calculations to see how much current flows through the device in the absence of a signal, and whether the device is healthy, whether the device is in saturation. And then step two, once we have confirmed all of those, we can go ahead and look at the small signal properties. So small signal analysis reveals the voltage gain and the input and output impedances. So small signal analysis. Now, what we will do in this case is actually go to step two first, understand the small signal properties of the circuit, its voltage gain, input impedance, and output impedance, and then we'll go and attend to its biasing considerations. How do we bias it? How do we calculate the biasing, etc. So we start from the small signal analysis. Okay, so in the small signal analysis, we would like to find the voltage gain of a circuit. How do we do that? Well, we draw the small signal model of a circuit and proceed, and we will do that, don't worry. But before we jump into that, let's make a simple qualitative observation that tells us something interesting about the stage vis-a-vis the common source stage that we studied before. So let me change the color of my pen, and then I will show you what happens. Let's suppose that the source voltage changes by delta V. In particular, let's assume that the source voltage goes up by delta V. This is the input, so it can go up, it can go down. Let's say a microphone signal comes in, and this goes up by delta V. All right. And remember that the gate voltage is constant. So what happens to the drain current of the MOS device? The gate voltage is constant, the source goes up. That means that VGS decreases. If VGS decreases, the drain current decreases. If the drain current decreases, what happens to this voltage? So we have a resistor here. We have VDD here. If we draw less current from this resistor, this voltage has to go up. Right? You remember that this voltage can be written as VDD minus ID RD. So when the source voltage, when the input goes up, VGS decreases, the current decreases, and that means that the voltage increases. So the output goes up by some amount. So that's an interesting point, because we see that this amplifier does not invert, meaning that its voltage gain does not have a negative sign in the front. In the common source stage, we have the negative sign. Here we don't. So that's one interesting difference between the common gate topology and the common source topology. It's not really a big deal in circuit design whether we have a negative or not, but this intuition is helpful in understanding how the circuit operates. I will see you next time.